Hi everybody, I'm going to go over acid chloride reactions in this video. So we're going to see how acid chlorides can be really helpful in terms of being a really solid intermediate to access a lot of different carboxylic acid derivatives. So if you have an acid chloride in hand, you can make anything that you want really, because it is the most reactive of the carboxylic acid derivatives. So it's easy to go downhill from that high energy, high reactivity intermediate. So acid chlorides, you can make anhydrides, esters, amides, doesn't really matter. We already know that it can make carboxylic acids, but generally you wouldn't want to hydrolyze an acid chloride to a carboxylic acid just because the acid chloride is usually so much higher in value in terms of reactivity. So generally we want to keep it in that reactive form and then make something else. So we're going to see how we can make these three things. So I've just kind of summarized the reactions to start. So we can make anhydrides, esters, or amides, okay, with acid chlorides. And you'll see that, in some cases, we've got stuff like pyridine, we've got extra of the amine over here when we're making amides. So those are really just in place to help you soak up the HCl that's produced in the reaction. And we'll see in the mechanisms where that comes up. Okay, so let's start with the anhydride mechanism, which is probably the easiest one. So we've seen various like acetate nucleophiles used when we were doing SN2 reactions and things like that. So we're going to see a very similar situation here where we've got our acid chloride. And I'm just going to use sodium acetate. So you're going to normally have some sort of counterion here, but really like just think any carboxylate is going to work for this type of process. So we're going to use our O- as our nucleophile here and then attack our carbonyl electrophile. Oops. Okay, so you already see that we're pretty close to our final product at this point. So all we need to do is break apart that tetrahedral intermediate. Oops, that's the wrong one. We're going to have the chlorine leave. Okay, and so the chloride is a better leaving group than the acetate. So once this attacks, I'm actually going to change that. So once it attacks, it is going to be fairly one directional, just in terms of like the chloride is better to hang around on its own than the acetate is. So we're going to see the formation of that anhydride, and then we're going to make NaCl, okay, as our byproduct. All right, so let's go to the ester mechanism. So again, we're going to use some kind of alcohol. I'm just going to use ethanol here, and we're going to put pyridine in. Okay, so remember, pyridine is not a strong enough base to go around and deprotonate alcohols. It's not going to do that. It can protonate things that are positively charged. So if an oxygen has a positive charge on it and an H, that's when the pyridine is going to come into play. But it's not going to deprotonate the alcohol at the beginning. Okay, so we are using a weak nucleophile to attack our acid chloride. And the reason we can do that is because the acid chloride is so high in reactivity. So it doesn't need a strong nucleophile. Okay, so we can just go ahead and attack right away. Okay, so then we get to this intermediate. At this point, we've got a tetrahedral intermediate that we can use. So if you want to deprotonate at this stage, I don't really care, that's fine. I tend to deal with this first, but it's really up to you which one you take care of at the beginning. Okay, so then we form Cl-, And then at this point, this is when our pyridine can come in. So you can do it at this stage, or you can do it over here. Doesn't really matter. Okay, so now our pyridine is a good enough base to go get this highly acidic proton. And this is pretty much a one-way trip. So this is a pretty good, like, irreversible step with the acid-base reaction, but also because the ester is a lot lower in reactivity than the acid chloride is. So it's harder to go back to, back to the acid chloride from the ester when we're starting there. Okay, so we also made as a byproduct pyridinium chloride. So that's what it's called when it's protonated. And we've got a chloride counter. Okay, so again, we're just kind of soaking up essentially an equivalent of HCl in this process, where we've got the H over here and then the Cl over here. And we're just kind of mopping that all up with the pyridine so that it doesn't get super, super acidic and really cause some problems. All right, so let's head on to the amide version. Okay, we're going to see a very, very similar process here. And we're going to have two equivalents of this. Okay, so just think about this as being in excess. So the first step, again, we don't need a strong electrophile. Well, sorry, strong nucleophile, because we have a strong electrophile. So we don't need to protonate or anything beforehand. We're just going to go straight on in. Okay, so then we end up at this tetrahedral intermediate. Again, if you want to deal with the acid base now, that's fine. Or you can deal with the, you can make the carbonyl first. That's what I'm going to choose to do. Okay, I've made my Cl minus now, but the best base that's around is my dimethylamine that I started with, not the Cl minus. So that is going to come around. Little dimethylamine here. Grab that H, give the electrons back to the nitrogen. That's a pretty irreversible step. And then I end up with my neutral amide plus a protonated dimethylamine with a chloride counter. So again, kind of soaking up that HCl equivalent that we've generated. So we need at least two equivalents of that amine, one to act as a base, one to act as a nucleophile. All right, so one equiv. All right, so the other one to be a base. So that's all the carboxylic acid derivative reactions. I feel like once you get the pattern down, they're really, really similar. So you can kind of, even if you don't memorize the exact mechanisms for each one, and I really don't recommend doing that, but get the patterns down and then you can figure out any mechanism that involves one of these reactions. Even if it's not one that you've like seen before, you can see the patterns and kind of figure it out from what you know. So have a great day, and hopefully make sure you ask any questions that you have, and I will see you all later.